this is an atom. You all know what atoms look like. You know what's in them. You know that in the nucleus they have protons, which are positive. They have neutrons, which are neutral. And around the outside, they will have electrons, which are negatively charged. Now, you need to know some interesting information about these three different particles: protons, neutrons, electrons. Now, you don't need to know exactly what their mass is or exactly what their charge is, but we talk about relative mass and relative charge. That just means we can compare them to each other. So protons and neutrons have a relative mass of 1. That means they're basically the same mass as each other. An electron has a mass that we tend to say is negligible. That means it's very, very small. So electrons are tiny. We're talking almost 2,000 times smaller than a proton or a neutron. So really, really not very significant. So we're going to ignore those when we're calculating the mass of an atom. We also need to know about charge. As I said, protons have a charge of +1, electrons have a charge of -1. That's very convenient. They're identical but opposite charges. Now, because an atom always has the same number of protons as electrons, that means it always has charges that cancel out. So an atom has no charge. If I start taking away electrons, that's no longer an atom, it's an ion, a charged particle. If I start adding electrons, that would also make an ion, just one that's negatively charged. The neutron, of course, has 0 charge. And that's what atoms are made of. And this structure is really important when we're starting to name atoms, because the number of protons tells me what element I'm dealing with. That defines what substance it is that this atom belongs to. So if, for example, I have 1 proton, that's always hydrogen. 2 protons is always helium. 3 is always lithium, and so on. Now, the way we write this is, if I give you an example of uranium, uranium has 92 protons. So we always write the number of protons there at the bottom. We can call it the proton number. We can call it the atomic number. And it tells you exactly which element it is, because anything with 92 protons is always uranium, and so it's always going to behave like uranium. We'll also write another number, and in this case I'm going to pick 235, and that tells me, well, that's our mass number. It tells me how heavy this nucleus is. And that is the number of protons plus the number of neutrons. So that tells me exactly how big this nucleus is. And if you take this number away from that number, you can work out that uranium-235 must have 143 neutrons. So the mass number tells me how many protons and neutrons together. The proton or atomic number tells me how many protons. Now, this is really interesting, because if I have alpha decay, if you remember, an alpha particle is made of 2 protons and 2 neutrons. So that means if something, some mystery element, is going to decay into some other mystery element by alpha decay, you'll notice that it's going to lose 2 protons. So that bottom number is going to go down by 2. And it's going to lose 2 protons and 2 neutrons, so the top number is going to go down by 4. And you can always spot alpha decay, because it will always end up with a nucleus that's 4 parts lighter and has 2 less protons. That means it's a different element. There are 2 other things we need to be able to deal with nuclear physics, and these are ways of getting energy out of the nucleus. First, it's called fusion. Now, fusion is really, really simple. All it is 2 small nuclei Hydrogen is the classic example because that's what most of the fusion in the universe is. So two small nuclei, and if you can get them to crash together hard enough, with enough energy, they will combine together and make one larger nucleus. If I crash two hydrogen together, I can get helium, and they will release some energy, which is thoroughly useful. Now, this is all that happens in stars. So inside a star, you have hydrogen that is gradually being fused to make helium. That's what gives a star light. It's the energy being released by this fusion reaction that makes a star bright. And actually, as a star continues, it will gradually start to fuse helium into heavier elements. And all of the elements in the universe have been made by stars and by supernova when stars explode when they die. But what you need to know is that fusion is two small nuclei crashing together to make one larger nucleus and releasing energy. And you need to know that that's what fuels stars. We do not use fusion on Earth. We would love to, because we have plenty of the raw ingredient, hydrogen, or some of the different isotopes of hydrogen. We have tons of that around. It doesn't produce any radioactive waste, and it could release a massive amount of energy that could solve our difficulties in finding energy sources. However, this reaction is very, very difficult to get started. It needs a lot of energy to put in, and at the moment the only fusion reactions we've managed need more energy to go in than we get out at the end. It's also very, very hard to sustain. How can you get something to burn like the sun and yet be contained in something that we've built? It's remarkably difficult. But if we crack that in the next few years, who knows, it could totally change how we deal with energy. Something we have managed to get to work is fission. Now, I'd advise you to learn these two words and learn how to spell them, because examiners are really keen that you don't get them confused. Fission is the opposite of fusion. It's one very, very, very large nucleus. And there are only two nuclei that we've managed to get to do this for us. One is uranium-235, and the other is plutonium-239. Now, one of these large nuclei, if I fire a neutron at it, and it absorbs a neutron, it becomes really, really unstable. And you've met some unstable things before. You know a little bit about radioactivity. But this is so unstable, it doesn't just give out an alpha particle or a beta particle or some gamma radiation. It splits into two, and we call that fission. That's all it means, an atom splitting into two. And it will split into two smaller, we'll call them daughter nuclei. So out of one very, very large nucleus, 235 different particles in there, it will split into two smaller nuclei. And it will also chuck out some neutrons, 2, possibly 3 neutrons. And you can see straight away what's going to happen is that those neutrons could go on to collide with other uranium or plutonium atoms, and that would start a chain reaction, that this would gradually get to be a bigger and bigger reaction, giving out more and more energy. And that's exactly what happens in a nuclear bomb. If we can control it by controlling exactly how many of these neutrons go on to cause another fission, then that's a nuclear reactor. And that's what we use in nuclear power stations. And it is thoroughly useful. It's a brilliant way of making energy, no carbon dioxide released, lots of fuel around, but it has some severe negative sides. It creates a lot of radioactive waste, which is very difficult to dispose of safely. It means that we've got some material around which could potentially be used to make nuclear weapons. And as we've seen recently in Japan, there's the potential for accidents at nuclear power plants to be very dangerous indeed. So fission has its advantages in using it to generate electricity. It also has some disadvantages. But what's really key is that you know that fission is one large nucleus being split into two smaller daughter nuclei, releasing some neutrons and some energy, and that we can harness that energy.